Polar can be a nice transformation, particularly if your region has some kind of circular symmetry or is easily expressed in terms of polar. But polar is not the only kind of transformation you might use. I just want to show you some examples of where another transformation might actually be a good idea. So if we look at this integral, of course the devil's always in the details of what the bounds of the region are, right? Because if the bounds of this region are complicated, then it's going to be a lot of work. So let's just look at the region that we're talking about. We've got these, we've got basically two pairs of parallel lines. So the first one is y equals negative 2x plus 4 and y equals negative 2x plus 7. That's our first pair. You can see both lines have the same slope, they just have different intercepts. So let's graph those two lines just to kind of get a picture of what's going on here. If I go up 1, 2, 3, 4 versus if I go up 5, 6, 7, I have these lines that for every one you go over, you go down 2. So this first one starting at 4, 1, 2, 3, 4, over 1, down 2, over 1, down 2, we get this line. Okay, and the other one is similar, it just starts up a little bit higher at 7, 2, 3, 5, 6, 7, so same slope, over 1, down 2, over 1, down 2, over 1, down 2, over 1. Okay, so there's our first set of bounds. And then these other two are both lines with slope 1, right? So one has an intercept of 1 and the other one has an intercept of 2. So, or of negative 2. So we can draw this line here, and then an intercept of negative 2 would be down here, right? So this is the region that we're talking about integrating over. Now notice this is kind of hard to set up with our usual bounds, because our usual bounds we tried to put either put the region between two horizontal lines or put the region between two vertical lines. But in this case, let's say we put it between two horizontal lines. For a particular value between those two horizontal lines, the equations that determine the range on the x values change as we go along. If you look at this intersection point here and carry that over, or look at this intersection point here and carry that over, you can actually see in this lower region you use this line and that line as the bounds. But then once you cross over this line up into this middle region, you use this line and a different line, right? Instead of using this line, you're using the other line that's parallel to the original. You cross over past this point and up in this upper region, then you're using those two lines. So really the bounds on x are different in 3 different locations. So to really set this up, we're going to use 3 different integrals. That's going to be kind of a pain. So it's a pretty simple region, but it's kind of hard. We'd have to set up 3 integrals in order to do the integral over that region. So we want to look for a transformation that will kind of straighten these out. One thing I noticed, since these are parallel lines, both of these have the form y plus 2x equals some constant, right? The first one is y plus 2x equals 4, the other one is y plus 2x equals 7. Now these both have the form y minus x equals a constant. This one, y minus x, is negative 2, and this one, y minus x, is 1. This gives me an idea for a transformation. If I set u to be y plus 2x, then being between these two lines is really saying u is between two constants, 4 and 7. If I set v to be y minus x, then y minus x being between these two lines, right, is the same as saying v is between two constants. So this would be a nice transformation. Let's say u is y plus 2x and v is y minus x. Now we have, if we look in uv space, this region is actually the region between these two vertical lines, u equal 4 and 7. 1, 2, 3, 4, 5, 6, 7. There's 4 and 7, so okay. And let's see, v is y minus x, so this is the region where v is between these two horizontal lines, negative 2 and 1. So down 2, up 1. The beauty here is that this is now a rectangular region. Now our issue is we want to do this integral in terms of u and v, but we need to know how will a small chunk of area here transform? What will its size be? What stretching factor is there that will change it. Now what we have so far are equations from x and y, right? Equations that will turn x and y into u and v. So we could easily find the stretching factor this way, but we need the stretching factor that goes from where we're doing the integral to the place we want the integral to represent. We need the one that goes the other way. There are two ways to do it. One way is to take your system of equations and invert them so that you have, instead of having u and v in terms of x and y, you have x and y in terms of u and v. In this case, that's not hard to do because I can see some combinations that will eliminate y and allow me to solve for x in terms of u and v, and I see a combination that will eliminate x and allow me to solve for y. So what I'm noticing here is if I take u minus v is going to be this minus that, right? Y minus y is nothing. 2x minus y is 3x. So it's pretty easy to solve for x. X is going to be u minus v over 3. It's also pretty easy to get rid of the x. If I take u plus 2v, u plus 2v is going to be y plus 2y, that's 3y. And 2x and negative 2x would be no x's. So I got rid of the x, and now I can solve for y in terms of u and v. Okay, so now instead of having the equations that start with x and y and give me u and v, I've inverted them so that if you give me u and v, I can easily recover x and y. Okay, then I can just calculate the Jacobian in this case. So I'm thinking I've got my outputs x and y, and I've got my inputs u and v. The partial of x with respect to u is 1/3. The partial of x with respect to v is negative 1/3. The partial of y with respect to u is 1/3, and the partial of y with respect to v is 2/3. I'll take the determinant of that first derivative matrix, and I get, let's see, 2/9 minus 1/9 gives me 3/9, which is 1/3. So I know that any region here in UV space ends up being 1/3 that size when it's over here, right? At least a tiny region would do that. Okay, in this case it's a linear transformation, so it's true for all of them. So this is my Jacobian, right? It's 1/3. So I can set the integral that way. But while we're here, we can see we didn't necessarily need to invert these equations, because if you can find the stretching factor the backwards way, if something gets stretched by a certain amount, then it's going to get smashed by the reciprocal amount as it goes back. Let's just calculate the Jacobian from this. So these are the wrong way equations, right? This is the stretch. If you calculate Jacobian here, we've got u and v as the outputs and x and y as the inputs. Partial of u with respect to x is 2. Partial of u with respect to y is 1. Partial of v with respect to x is negative 1. Partial of v with respect to y is 1. And so we take the determinant of that. In our Jacobian determinant, we have 2 minus 1 would be 3. You see the relationship there? We know that's always going to be the case, right? If it's getting smashed by 1/3 this way, then it's going to get stretched by 3 that way. So you could have determined that the Jacobian that you wanted was 1/3 because you had the stretching factor this way of 3 would have to be a smashing factor of 1/3 in the direction that you really needed it. So you could have obtained the 3 and taken the reciprocal to get that conversion. Okay, now I think we're ready to set up our integral here. We have v over here. V is going from -2 to 1, and u is going from 4 to 7. And we need to convert this function, and then we can integrate du dv with our stretching factor of 1/3 there, our Jacobian determinant, 1/3. Okay, if I had set this up, if I had switched, say, the order in which I wrote these, the only thing that would happen to the determinant might be to change its sign. So we always take the absolute value of the Jacobian determinant anyway. So even if you got -1/3, you'd still put 1/3 in here because that's the absolute value. I happen to notice that this has a pretty nice form. This actually factors to, let's see, what if we try x, 2x plus y and x minus y. That is 2x squared minus 2xy plus xy would be minus xy minus y squared. So this thing that we're integrating is actually 2x plus y times x minus y. But 2x plus y is actually u. So this is u, and x minus y is v, right? Well, v is y minus x, so x minus y would be negative v. So we have this integrand actually is negative uv. Pretty handy. Now that just happened to be a little gift in this problem, that it was easy to convert that way. We also could have just converted back to u, turned x and y's into u's and v's by using this system of equations that we had solved in order to find the Jacobian. So you could just take every x and replace it with u minus v over 3, and take every y and replace it with u plus 2v over 3. Crank it all out and keep multiplying and multiplying and multiplying, you'd come down to minus uv. So, okay, now this is pretty simple integral to do. We're doing the first integral is with respect to v, so why don't I can pull all the constants. I can pull the 1/3 all the way out, and I can pull the v at least out this far. I'm going to pull the negative out too. And then I have the integral from 4 to 7 of u du inside the integral here. But if you look at this, the integral from 4 to 7 of u du, you're going to take an antiderivative of u and evaluate at these two constants. That cannot depend on v, so this is going to be constant as far as v is concerned, so it can come out in front. So we get negative 1/3 times the integral from 4 to 7 of u du times the integral from negative 2 to 1 of v dv. Okay, so to finish off this problem, we've got negative 1/3. Antiderivative of u is 1/2 u squared between 7 and 4. So that's going to be 49 over 2 minus 16 over 2. And then the antiderivative of v is going to be v squared over 2 between 1 and negative 2. So v squared is, if v squared is 1, if v is 1, then we get 1 over 2 minus negative 2 squared is 4 over 2. So what do we have here? We have a negative 1/3. 49 take away 10 would be 39, take away 6 would be 33. So we have 33 halves. And then this is times 1/2 take away 4 halves would be negative 3 halves. So the negative 3 and the negative 1/3 cancel, and we get 33 over 4 for the integral. So the transformation, although it was a little bit hard to find the Jacobian for the transformation actually made the bounds much nicer, and in this case it was kind of a special gift that the function became simpler as well. That doesn't always happen, but it does kind of happen sometimes with problems from the book.